when we have an electrochemical cell set up, the main piece of information that we will look for is the cell potential, which we'll label as a capital E subcell. And this is the value that will tell us whether it's galvanic or electrolytic, and essentially what the potential difference is between the two electrodes. So this value for the cell potential ultimately depends on the relative tendency of the reactants to undergo oxidation or reduction. It also technically depends on temperature and concentration. So we will have a set of standard conditions, which we have used many times before. So standard conditions, everything has a concentration of 1 molar. Any pressures are 1 atmosphere. The temperature is 25 degrees. Technically, what we are calculating is this E cell with the little circle that we use to indicate that it's under standard conditions. Okay, so I have just a couple of examples of what these values look like for two reactions. So for the reaction zinc solid plus copper 2 plus turning into zinc 2 plus and copper solid. We're going to compare this to nickel reacting with copper. So nickel solid plus copper 2 plus turning into nickel 2 plus copper solid. The first reaction of zinc with copper 2 plus, the standard cell potential is plus 1.10 volts, and for nickel solid with copper 2 plus, the standard cell potential is plus 0.62 volts. So when you put zinc with copper, the potential difference is larger. And so what this is telling us is that zinc has a higher tendency to be oxidized than nickel. So we never put zinc and nickel together in the same reaction, but by looking at how each of them reacts with copper, we can get some information about their tendency to be oxidized. Okay, so this standard cell potential, I mean any cell potential, but right now we're talking about standard, is for the whole cell. So the entire piece with the anode and the cathode. So the question is, how do we get information about the cathode or anode individually? So how do we get potential values? For the cathode or anode individually? And the answer is that we use a standard. So the standard that we use for this is called the standard hydrogen electrode. And it is 1 molar hydrochloric acid. It is 1 atmosphere of H2 gas and a solid platinum electrode. So what we do is we can set up any half cell against the standard hydrogen electrode and then measure the potential difference, and then we set the hydrogen electrode to be 0 volts and measure everything relative to it. So we always make the standard hydrogen electrode the cathode, and we set it to 0. So the standard potential for the cathode will be equal to 0.00 volts. And then we look at the reading that comes out of our voltmeter, and we can use a little bit of very easy algebra, well, just mostly straightforward math, to get the standard cell potential for the anode for whatever we've set it up against. So, then I should give you the reaction that's happening at the standard hydrogen electrode, is that it's 2H plus 2 electrons turning into H2 gas. So let's look at calculating this for an example cell. And what I want to set up for the example is our zinc half cell, so zinc solid and zinc 2 plus aqueous with the standard hydrogen electrode. So H plus aqueous, H2 gas, and solid platinum. So when we set this up, we measure, under standard conditions, a cell potential of plus 0.76 volts. So the standard cell, so E cell, this is what we measure. And we're setting the cathode equal to 0, but we don't yet have an equation for this. It is obviously on the equation sheet, but what we end up looking at, it's just a final minus initial, right? We're looking at really a potential energy difference here. And what that translates to is that it's the cathode minus the anode. So we measured this E cell value. The cathode value, that's the standard hydrogen electrode, so it's going to be equal to 0. And then we will be able to calculate the value for the anode. So in the case of this zinc cell that we've set up, just rewrite this. My standard cell potential is the cathode value minus the anode value. This is the equation that you'll find in your equation sheet. For the zinc cell, plus 0.76 volts is what we measured. The cathode, as our standard, is what we're setting equal to 0. So if we solve for the potential of the anode relative to our standard, we get negative 0.76 volts. So what this is telling us, a couple of things. Our anode is at a higher potential energy than the cathode. Which means that the reaction is spontaneous under standard conditions. Okay, so some extra good news is that obviously we don't have to set up all of these and measure them in order to use them. That has been done for you already. And standard electrode potentials can be found in the appendix. So that's the great news. The confusing news is that when you go to the appendix and you look up what we just did, so this zinc half cell, you get zinc 2 plus 2 electrons turning into zinc solid. And it will list a standard E equals negative 0.76 volts. Okay, this is written as a reduction reaction, but we just used zinc as the anode half cell for oxidation, and we got the negative 0.76 as our answer when we looked at what its potential would be relative to the standard. So that's the unfortunate confusing news, is that all of the standard electrode potentials are written for reduction. So every single reaction here, so we can just see another example. So copper 2 plus 2 electrons turning into copper solid. If you look this up, you'll see that it has a standard E of 0.34 volts. Let's just put this into words. All electrode potentials are written for reduction. However, these potentials will follow the rules that we have gotten used to seeing for things like delta H and delta G, where if you flip the reaction, you change the sign. However, we don't have to do that. All you have to do is use the equation that's given, because it takes care of the sign change for you. And we are going to look at an example of this. So our equation does the sign change. So all you have to do is find the value for the correct reaction and plug those numbers into the cathode minus anode equation. Okay, so as an example, what we're going to do is calculate the standard cell potential for this reaction, which is PbO2 solid plus 4H plus tin solid turning into Pb2 plus 2H2O liquid plus tin 2 plus aqueous. Okay, sorry, got a long one this time. So we need to identify the anode and the cathode. So the oxidation half reaction that's happening here is that tin is turning into tin 2 plus plus 2 electrons. So this is going to be my anode. And the reduction half reaction is the PbO2 plus 2 electrons turning into Pb2 plus. Now there's some other pieces in this reaction, the H plus, the H2O, that are there for balancing, but as long as we've identified the correct oxidation numbers for the things that are changing, we'll have the correct half reactions when we look them up in the appendix. All right, so we go to the appendix, and what we find are the following reactions. Tin 2 plus 2 electrons turning into solid tin has an electrode potential of negative 0.14 volts. And then we see PbO2 plus 4H plus 2 electrons turning into Pb2 plus 2 H2O. And this electrode potential is plus 1.46 volts. Okay. So in the appendix, we find the other pieces. So the H plus is there, the H2O is there. If we added these back together, flipped in the appropriate way, the electrons would cancel out. So this looks great. And, right, my oxidation reaction is written as a reduction, but I don't have to do anything other than plug in the numbers because my equation will take care of the sign change for me. So my standard cell potential, remember, is the cathode value minus the anode value. So 1.46 minus a negative 0.14, and I get a cell potential of 1.60 volts.